today with combinations of aluminum indium gallium phosphide technology, aluminum gallium arsenide technology, and gallium nitride technology. We can span wavelength ranges from about just a little over 200 nanometers all the way into the infrared. With the ability to cover the entire visible spectrum, LEDs have become commercially important in a wide variety of applications. Perhaps the most important one that's emerging today is lighting applications, both for commercial devices like LCD TVs, LCD TV monitors, the computer monitors, and handheld portable devices. So we all know that LEDs are used there. Solid-state lighting is becoming a very large application for LED technology, and that takes us up to where we are today. The operating parameters of LEDs are rather challenging from an electronic, from a thermal, and from an optical standpoint. Nanotechnology can play a role in all of these particular areas. Finally, and I know that you're interested in this research yourself, nanotechnology is appearing as a core technology of thermal management.
The heat transfer process at the nanoscale can be fundamentally different from that occurs on the macro scale. On a macro scale, there are a lot of defects in the material, and so as the heat tries to pass through the material, it ends up scattering off of these defects, which means that we normally describe heat transfer using a diffusive type mechanism. At the nanoscale, where things are a little bit more ordered, there's the possibility for having the heat move coherently through the material, which is generally called ballistic transport. Management is a really broad topic, but in general it means being able to sort of move around heat so that you can control the temperature of an object, whether the object happens to be an inorganic material like a microprocessor or something like your body. Application, really, we're looking at cooling of microelectronic components, and there a thermal interface material is used to enhance the heat transfer from one sort of solid surface to another solid surface. But in microelectronics, a TIM, or thermal interface material, has to serve two purposes. It's got to be very efficient at conducting heat from one surface to another, and it also has to serve as a sort of flexible adhesive layer so that as the surfaces change temperature and expand and contract, this thermal interface material will be able to absorb the stresses as well as conduct the heat.
Historically, people have always done that to get both thermally and electrically conductive materials by taking microscopic silver particles and mixing them in epoxies or silicones and trying to get enough particle-particle contact to improve both the thermal and the electrical properties of the die-attached material so the LEDs would work both electrically and thermally. However, the micron-sized silver particles, or actually tens of micron-sized silver particles or larger, don't always give you the optimal thermal interface.
This is a project that's sponsored by IBM, and I work with Professor Borka from the Mechanical Engineering Department. And our idea is actually to go ahead and make a composite material whose matrix is a flexible polymer. And inside we have a network of sort of metal wires that span throughout the entire structure. And the metal wires serve to carry the heat, and the polymer serves as the adhesion layer and the layer that also goes ahead and relieves the stresses between the two materials. Basic basic idea is that we want to be able to self-assemble this high thermal conductivity network within the matrix of the polymer. And one of the easiest ways of doing that is to use small metal nanoparticles that can find one another in the polymer matrix and then fuse together by sintering to form a composite wire inside. That's something that's a lot more difficult to do perhaps with a graphene sheet or carbon nanotube, because it's difficult to self-assemble those systems into a single layer that would be on the order of microns or so in length. Our process involves using coated silver nanoparticles. The coating is there primarily to prevent an oxide from forming on the silver particles and allow them to sinter. And so what we do is mix the particles in with our polymer precursor. We then go ahead and heat the mixture up, and the first thing that the heating process does is to remove the coating on the silver particles. Then, because silver doesn't actually like the polymer, it tends to want to find other silver nanoparticles, and so it spontaneously assembles into chains. As we heat the process up further, we're able to go ahead and fuse the chains together and also cure the polymer so that we get a solid mass. So far, we've been actually pretty lucky in that we're able to make nanocomposite materials that have thermal conductivities that might be 50 to 100 times that of the best TIM materials that are out there today.
Our industrial membership, which supports our research in part of the ERC, has required us to look very carefully at packaging issues for LEDs, including thermal management. So they understand it's a big problem. They understand that new technologies are needed, and we are starting to address that with researchers such as yourself to look at exactly how we can move some nanotechnology into new die-attached materials and new architectures for better thermal management in LED systems.